Okay, so this hour we will be discussing the gyroscope, but before beginning the gyroscope, do you have any questions about our previous example? Okay, one thing that you should always pay attention to is the point with which you are, relative to which you are calculating the angular momentum. For example, the point A in this example is fixed. There might be, this point A is not really a point fixed on the road. That point A just happens to coincide with the road before the collision. Once there is a collision, the road starts moving, the point A stays there. It's not changing.
A point is fixed. That must be a force.
To fix the point A. Well, this is a mathematical point. It doesn't have a mass. It's not a physical object. It's not fixed on the road. It's just a mathematical point which doesn't have a mass. It doesn't even exist mathematically or physically. Other questions? The point, your reference points are always fixed. They do not move. Okay, so let's start the gyroscope, this problem. This example you had already seen several times. So if you just take some object with a large moment of inertia, it doesn't have to be a disk, but the crucial thing that its moment of inertia should be large. The easiest thing to do is to have a ring, because the mass is far away from the center, so that this moment of inertia will be large. Now if you give it an initial angular momentum, it doesn't fall. Now, if the angular momentum is not large, if it is very small, it does fall. So at least there should be some critical limit at which if you give it a large enough angular momentum, it will rotate without falling down. So why does it happen? Now let's study the motion. So we have this large mass. Well, ideally, you would attach it through a longer rope, longer stick. So this is the suspension point. You suspend it from this point, and here you have this wheel. This is what we call the gyroscope. You give it an initial spin so that you will get some angular velocity in this direction. Now this is the initial configuration. So I'm just holding both ends. And at the instant that I release this, one of my hands, it starts this so-called precession. The gyroscope, this motion, this rotational motion is what we call the precession. So at this, now the reason why I call it at the instant that I release, because you see, the motion it does is, it is rotating around this axis, this horizontal axis, but at the same time, since it's precessing, it is rotating around the vertical axis. The angular velocity vector of this object is not exactly horizontal. It is in fact, due to its rotation, it's also rotating around this vertical axis. But we will assume that it is rotating so fast around this axis that we can ignore the vertical component of omega. So that's that's the reason why we should give it an initially large angular velocity. Unless we give it a very large angular velocity, the wheel will just fall down, as you would expect. So the wheel is rotating fast enough so that we can ignore any other component of angular velocity. Now, what is the direction of the angular momentum of this object? Since it's quite a symmetrical object, the angular momentum will also be exactly in the same direction. This is that, which is equal to I times omega. Now, this I is for rotations around this axis. What is the torque? What are the forces acting on my object? Gravity. Well, it will be acting over here. There is the weight. Are there any other forces? Friction, ignore friction. Which tension? The stick. Well, let's just take the rod plus my stick as my whole system. So this is my whole system. Which normal force? The suspension point. What is the direction of that force? Vertically up. Well, let's do the experiment. Where is the center of mass of this object? Somewhere over here. What is the motion of the center of mass? Uniform circular motion, more or less uniform. So what is the acceleration of the center of mass? What is the direction of the center of mass? Acceleration, linear acceleration. Not angular acceleration. Well, for rotational motion, the acceleration only is towards the center. Unless there is tangential acceleration, there is an acceleration towards the center. But central acceleration is horizontal. And we had already said that the acceleration of the center of mass is only due to external forces. So if the force acting at this rod at this point was vertical, what creates this central acceleration of the center of mass? The lesson of the story, the force exerted over here is not vertical. It is, at this instant, it is somewhere in this direction. You stay there. You stay. You're silent? Patient? Okay, so observe the direction of the string. Now it is almost vertical, right? It is vertical. Let me start rotating. You stay where you are. Okay, it is vertical. Well, it will be hard to observe from there, but it's not vertical. It tilts a bit. It's not easy to observe from this one, Well, if you look at it from close by, the string is not vertical, so the force over here should be it should have a horizontal component. So this is the force. We don't know what that force is. But that's not a problem if we calculate the angular momentum and the torque relative to that point. So that is what we will be doing. We will be calculating the angular momentum and the torque relative to this point only. So what is the torque? Let's say this is the z direction. The torque relative to this point A. This force doesn't create any torque. Just because we don't know what that force is not important, because it is acting at the point 0. The torque is 0. It's the weight, or let's say this is our r vector, r cross w. First of all, what is the direction? Okay, this is r, this is w. Just imagine r is rotating towards w. It's into the screen. So that is the minus z direction. And the magnitude, or whatever the length is, times mg. What is the angle between the two? 90, sine of 90 is just 1. So this is the torque we have. So we already know that the torque is dl by dt. It's the rate of change of the angular momentum. So if you have the angular momentum at a given instant is L0, at the next instant it will be L0 plus the torque times dt. So if you just wait for a very small amount of time, suppose this is the initial angular momentum, you wait for a very small amount of time, this is how much the angular momentum changes, and hence the final angular momentum is just L0 plus tau times dt. Now let's look at certain limits. Let's say that initially it's not spinning. So there's no angular momentum. And we want to create some angular momentum in that direction. How can we do that? If it is not spinning, and we want to have some angular momentum in that direction, how can we do that? Just rotate it like this. It will be falling down. It's just a falling motion. So it's rotating in this sense, which will create some angular momentum in that direction. So if you just release it like that, without any rotation, initial rotation, this equation tells me that the wheel should just fall down as we expect. And that is what happens if there's no rotation. Now, but the problem is if you rotate it fast enough, now there's already an angular momentum in this direction. If it would fall like this, you see the initial angular momentum, if it would fall down, you will get this angular momentum. That means the angular momentum changed in the downward direction. But we don't have a torque that is pushing it, that would change the angular momentum in the downward direction. So it would contradict this law over here. It will contradict with this one. If this would fall down, it will be contradicting with this law because there is no torque in the downward direction. And falling down means angular momentum would gain some downward component. So it cannot fall down. If you have an initial angular momentum, let's look at from the top view. So this is the suspension point. We have the roll. Here there is the wheel. This is the direction of omega. So initially, this is L. Now, after it starts rotating, there are two components to the angular momentum. One is due to this rotation, but the other one is due to this rotation. The wheel is also rotating like this, so there is also a contribution to the angular momentum due to this rotation. But we will assume that it is rotating so fast that the angular momentum due to this rotation is negligible. But if it is negligible, the angular velocity does not change. The angular velocity of the wheel is constant. So while it is rotating, the magnitude of the angular momentum, which is nothing but I times omega, but omega doesn't change. So during this precession, the angular momentum of the wheel doesn't change. So this is the initial angular momentum, let's say. After it precesses, there is a torque in this direction. So this is the change in the angular momentum. Torque times dt. The final angular momentum is this one. L initial, the magnitude of L initial is equal to I omega. The magnitude of L final is I omega. So they have both the same length. Now this is, let's say, the d theta. In a very small amount of time dt, it just rotated by d theta. Now we can just look at this one. This side and this side, they are both equal to I omega. The length of this side, which is tau dt, but we had already calculated the torque. It has a magnitude mgr. This should be equal to L times d tau, which is I omega d theta. Sorry, not that. So this is d theta, how much the gyroscope or the wheel precesses in a time dt. And from this one we can calculate that d tau or d theta by dt, which we define as the precession angular velocity. This is equal to mgr over I omega. Now omega p is the precession angular velocity. Now there is one prediction we can test with our setup over here. Well, I have a single wheel, so I cannot change the moment of inertia, I cannot change the mass, I don't have a long stick, I cannot change R, but I can still change omega. So the smaller omega is, the precession frequency should be larger. Let's give it a try. Let's see if it will work. You stay still. So let me first give it some small angular velocity. Okay, that's the initial angular velocity, angular precession frequency. You stay put. Let me give it a larger angular velocity now. Now it's much slower. At least one prediction seems to be satisfied. Okay, now we can stop it. So is it clear, first of all, why it cannot fall? If it falls down, it will contradict this equation. Okay, that is one thing. Of course, then the question is, why doesn't it fall? I mean, why should it care about this one? Why doesn't the center of mass of the system go down? What prevents the center of mass to go down? This one over here. The force that you are exerting. Now this, you see, the total force acting on the system, which will determine the acceleration of the center of mass, is this force plus the weight. So if you give it a spin, it just turns out that this force changes in such a way that it doesn't let it go down. And this force also creates the necessary central acceleration, centripetal acceleration of the center of mass, so that it will just carry out uniform circular motion. Of course, there's still the question, why doesn't it fall down? I mean, we had studied the Newtonian dynamics for point masses. All the points on the wheel are feeling a force in the downward direction due to gravity. So how come this force, let's say, knows how much it should be so that it will prevent the center of mass, which is over here, to fall down? Question?
Yes, my question
Yes.
is, what happens if we try to do this in the space? If it will rise or stay?
So your question is, you have this wheel in empty space.
Yes.
So you see, the precision here is created by the torque due to the weight. If there is no weight, there won't be any precision. By the way, this is also the reason why the bicycles can go in two wheels. So let's just imagine that you are riding your bike in the forward direction. Okay, so let's give it a spin. Let me use this one. So you're riding your bike. And suppose that at some instant you just lose your balance and you lean to your right. So that you will be exerting a larger force to the left of the wheel than to the right of it. So this is, you are going on straight line. Suppose you exert a larger force, so this is what the front wheel does. Rather than going sideways, the front wheel just rotates. You were leaning right, the wheel just turns sideways towards the right. So if you are going straight, if you lose your balance and you go to your right, you just change your direction. The wheel just rotates towards the direction that you were about to fall down, and then you just regain your balance. If you would go the other way around, if you lean towards the left, the wheel just rotates towards the left by itself. You don't have to do anything. And in fact, this is also how you can ride a bike without holding the handles. Because if you want to turn left, the only thing you have to do is just lean left. The front wheel, if it is spinning, it will do the rotation for you. Yes, any questions? Now, I will send you a link of a video which explains how, if you start from Newton's dynamics for the point masses, you can still understand this rotation. It's a bit more complicated to do, but it can still be done, and I hope it will be answering your questions about this gyroscope. The basic idea is that, let's see, if this is rotating like this, different parts should accelerate differently if this is to fall down. There should be internal forces acting on your system, and those internal forces would not be so symmetrical. Gravity is quite symmetrical. I mean, one thing, if you want to understand this, you shouldn't so much concentrate on the gravity. Gravity is symmetrical, and it will cause this thing to fall, try to cause this thing to fall down. What prevents it from falling down, what prevents what causes this suspension point to exert a force in that direction is mainly internal forces acting between different parts of the system. And that clarifies why the gyroscope persists. In fact, historically, the gyroscopes were also used to find your way in open sea. Because the main problem over here is if you have this gyroscope, if you change its or try to change its orientation, it will resist you. So you just start the wheel spinning quite fast, and then unless you are exerting huge forces, its orientation will be fixed wherever you go. So that would allow you to determine the orientation of your ship, for example. Also in empty space, it's also used. You can use such a flywheel, for example. That's also another example. This is just a flywheel. If you are, let's say, you are in empty space and you want to change the orientation of your rocket, the only thing you have to do is just rotate your flywheel in one direction. So to conserve the total angular momentum, the remaining of your rocket will be rotating in some other direction. And once you stop your flywheel, the rocket will also stop rotating. So you can change the orientation of your spaceship without using any fuel, except the one necessary to rotate your flywheel.
In this example, this force, because of this force, this object doesn't move.
True. This force you mean?
Yes. And it's affected by the angular curve.
True.
How does it affect?
Well, you see, the rotating object, that was the part. I will be sending you a link where there's a video which nicely explains how these internal forces play their game. If you are giving this a rotation, if it tries to fall down, you see the top point. Initially it has a velocity in that direction. If it is falling down, it also gains a velocity in the, let's say, downward direction. So that is the direction of the acceleration. So this top point should be feeling a downward force due to something. But that it will also exert an upward force to other things. Now if you look at this point, that point is moving down. Now as this is rotating, initially its velocity is downward. At some point it's not straight downwards, it makes an angle. This is the center of force that is necessary. But furthermore, if you are tilting it down, it gains a velocity in this direction, this point. That means there is a force acting on this point in this direction. But that mass over there is creating a force in this direction if it is rotating like this. So just take this mass, there's a mass over here. That mass, if this is falling down, if it's trying to fall down, that mass over there needs to feel a force in this direction. But that means that mass will exert a force in the opposite direction to the rest of the system. So that point exerts a force in this direction. If you do the same thing over here, this point would exert a force in this direction. So the net effect is that this thing turns around like this, if it is trying to fall down. Now, is it trying to, in this gyroscope motion, you have seen that it's not falling down. Let me give it an initial spin. Well, it's not falling down, so it seems as if this my argument that as this is falling down, there will be such rotating effects is not relevant. But if you treat this problem precisely, and here we made many approximations. Now, the actual motion of this gyroscope, you see, this is the gyroscope will be moving on the surface. Just imagine this point, the distance of this point from the suspension point is fixed. So that point can be anywhere on this sphere. As this is precessing, it is not actually going over such a circle, but that point is mainly making such a motion. Depending on your angular velocity, the energy of the system, etc., it will be either making this motion or this motion. These are what's called the nutation. Well, this is just general information. I mean, you are not responsible for all these, but the exact motion of the gyroscope is much more complicated, so it makes such a weird motions. But in our approximation, if you have a very large angular velocity and you create a large angular momentum in the direction of this rotation axis, then this is precise enough. You don't see all those wiggles. They are very small. I will send you the link. The link explains it in a more clear manner with illustrations. This one. This one. I'm just looking at this triangle over there. Well, this length and this length, they are equal because they are both equal to I omega. And this is that isosceles triangle. It's a narrow one, very narrow one. This d theta is very small. So, okay, these two lines are basically on a circle since they have the same length. But you see, this arc length over here is almost equal to the length of that vector over there. But the arc length is just the radius times the angle, L d theta. The length of the vector is just tau dt, which is mg times r times dt. So I have mg r dt is equal to I omega d theta, or d theta by dt, which we call the precession angular velocity, is equal to mg r over I omega. So the larger the angular velocity, the slower the precession should be, and that is what we have tested. Okay, sorry for the typo.
Benim asıl sormak istediğim şey şu. Buradan yol açan şey gravity, bunu engelleyen şey de gravity. Yani uzayda olduğu zaman gravity olmayacağı için uçak ve durumun olmayacağını düşünüyorum.
Now this is not rising up. This is just rotating like this. But you see, there are two things in fact. In this treatment, over here, we calculated the angular momentum and the torque relative to the point A. And we have seen that due to the torque created by the weight of the object, this gyroscope precesses. We could have done the same treatment by taking our reference point somewhere over here, let's say at the center of mass. Then the torque relative to the center of mass would not be due to the weight, but will be due to this force over here. Now, in empty space, the weight will be zero, this force will be zero. So there won't be anything creating the torque. Since there is no torque created, the angular momentum will not change. In fact, that is why you can fix a given direction in empty space by using a gyroscope. It doesn't change its direction. I mean, you can model empty space as a freely falling object, and if I hold it with one hand, it precesses. If I release both hands, it doesn't precess. It just goes down. So both the weight is necessary and this force is necessary. So there should be and the forces should be such that you create a net torque in your system. Without the torque, there won't be any precision. Other questions? Okay, so see you on Saturday. We have the exam. The exam will be at the same time in almost exactly same places. I will just change the place of one or two of you. Just check it before coming to the exam.